Good morning to all of you. I welcomes to all in our lecture series on Statistical Mechanics, that is your core paper 14, belongs to 6th semester BSc syllabus. In our last class we have been discussed about entropy of a perfect gas using classical microcanonical ensemble. In detail we have been discussed the derivations, we discussed up to this much we done with a single video, and then after up to this much explanation of this one also, okay, single video. Then another video we done for thermodynamical quantities of an ideal or perfect gas. Okay, up to this much another video we have been done. With two videos we completed this topic. Okay, here thermodynamical quantities, entropy, internal energy, relation between T and P, and chemical potentials. Okay, in our today class we are going to be discuss partition function for canonical ensemble. That was microcanonical ensemble. Here we have to discuss canonical ensemble. First we have to discuss what will be the partition function for canonical ensemble. Then we have to go for the perfect monoatomic gas in canonical ensemble, whatever we discussed in our last two classes, that is your entropy of a perfect gas using the canonical ensemble, microcanonical ensemble. Okay, here also we are going to find out the entropy in case of canonical ensemble, that is your first we have to find out its partition function. Then by using partition function we have to find out the entropy here. Okay, and also another thermodynamical quantity, Helmholtz free energy and internal energy. These things we are going to discuss in this video. In the next class we are going to discuss grand canonical about grand canonical ensemble. So today class we are going to discuss perfect first we have to discuss partition function for canonical ensemble, then we have to go for the perfect monoatom gas in canonical ensemble. So before we have to start our today's topic, I want to share something to you regarding this topic, entropy of a perfect gas using classical microcanonical ensemble. Here I forgot to say that what will be the partition function in microcanonical ensemble. Here you can see today class we are going to discuss partition function for canonical ensemble, but in that class I forgot to say that what will be the partition function in case of microcanonical ensemble. You just watch, I am going to be discussed here. Okay, see, you just recall your previous class where we discussed partition function. Okay, partition function is a function, carefully you have to watch. Partition function is a function of an ideal gas or a molecule, that will be a gas or for a molecule, which describes, that means partition function is going to give the information, partition function which represents. Okay, so what the partition function represents? The distribution of molecules or molecule of the gas among its various energy level. Okay, suppose and which is represented by the symbol Z that we have been studied. Suppose this is your container, suppose this is your gas container. Now for our easy understanding we have to consider only a single particle, this one will be inside, single gas particle, or you can say gas atom. Okay, single one. So so this gas atom inside this container, whole vessel, and this vessel is divided with large number of compartments, right? And further, the large number of compartments again further divided into the cells, different cells. So this is compartment 1, 2 up to k, and each compartment can be divided by large number of elementary cells. Okay, elementary cells. So for this compartment 1, it will be G1, it will be G2, G3, for K, G3. These things we have been discussed when we discussed about microstate and macrostate, right? Now again I am going to be read this definition. Partition function, that is your Z, what is going to be represent? It will represent the distribution of molecules or molecule, that is your this one, among its various energy levels. See, these cells, whatever we have been considered for each compartment, these are nothing but called as your microstates, that already we have been discussed in detail. Okay, these are called as the microstates. Each and every cells is called as the microstates, or the so-called energy levels or energy states. So each and every cell will be called as microstates or energy states or energy level. Now this particle is going to be distribute among these microstates, or you can say energy states, or you can energy level. So the function or any mathematical expression, not expression, any mathematical function, a mathematical function which will represent the distribution of a molecule among these all the microstates or energy levels or energy states, that will be called as your partition function. Okay, now see, this partition function directly depends upon what? You just carefully you have to watch. Suppose this compartment 1, G1 subcells. Suppose G1 is, suppose we have to consider 10. Initially it was 10. What will be the distribution of this one for this compartment? You just imagine. Okay, so this compartment 1 having 10 cells initially, or 10 levels or 10 energy states initially, and this particle is going to be distributed among these 10 cells. You just imagine what type of. Okay, now suppose this G1 increased to 30, the distribution will be same, the distribution will be different. So one particle is going to be distributed in all the 10 cells, then the probability will be, we know that suppose this will be, so here one particle or one molecule is going to be distributed among 10 various cells or energy states. How many ways? 10 ways. Okay, if these cells number of these cells, suppose it is increased to 30, so how many ways it has to be distributed? 30 ways, right? That means whenever the energy state increases, along with the distribution of this particle among this state also changed. So increased, it will be increased, decreased, it will be decreased, or generally we can say it will be changed. That means the distribution which represents Z, or the so-called partition function, is directly depends upon whom? Is directly depends upon number of energy states. If number of energy states is going to be changed, the so-called partition function is going to be changed. So the partition function is directly related to the number of states. Okay, now come to the microcanonical ensemble and its corresponding partition function. Microcanonical ensemble. Okay, here In case of your microcanonical ensemble, you can refer the first class, our first class. I'm going to show you. Wait 1 second. This is your first class information about microcanonical ensemble. That means each and every system or phase point. This is the system or phase point, or we can say the microstate in the phase space, right? In this case, all the energy states are distinguished. They are not linked with each other, means there is no exchange of energy. They are separated energy states. Correct? So separated energy states means for the microcanonical ensemble, the so-called partition function is nothing but directly depends upon the number of states present in the ensemble. Okay, if number of states is, or the so-called microstates or energy level is going to be changed, on the base of that partition function is going to be changed. That means partition function in case of microcanonical ensemble is directly related to the number of microstates. Directly related number of microstates. Clear? Now come to your note, last class note, this one, entropy of perfect gas using classical microcanonical ensemble. In this case, you can see del tau represents what? A hyper volume in between E and E plus D, one volume. It is hyper volume. Suppose this is the hyper volume, which is in between E and E plus D, right? Number of quantum states, second line it is written, number of quantum states or microstates or energy levels in the energy range E and E plus D will be how much? Del tau by h to the power 3n, whenever n is the total number of particles. Clear? So this represents what? This represents what? Number of quantum states. In case of microcanonical ensemble, what we discussed, number of separated systems or phase points is nothing but your microstates, because they are not linked with each other thermally. Energy not exchange. These are separated points, separated energy levels. So that you just so here we can easily conclude that in case of microcanonical ensemble, the partition function is nothing but microcanonical ensemble. Partition function will be nothing but your del tau by h to the power 3n. Del tau by h to the power 3n. So this is the partition function, what I forgot to discuss in the last class. Okay, so what we discussed here now, you can write a write-off somewhere in your note to further study in your future. Okay, and in latter you can follow the note. In latter, this del tau by h to the power 3n is represented by w. Okay, w. So in case of microcanonical ensemble, the so-called del tau by h to the power n is nothing but called as the partition function, or the w, so-called w, is called as the partition function. Okay, now this is one of the interesting things I am going to tell to you. See, later on you can check your note that w is called as statistical entropy. Okay, now you can ask, sir, the w is called as partition function, again w will be equal to statistical entropy of this microcanonical ensemble. Yes, in case of microcanonical ensemble, the number of quantum states or microstates is nothing but called as your statistical entropy, or the so-called partition function. Also you can say that partition function, that means Z microcanonical ensemble is nothing but sigma that is your statistical entropy is nothing but W. All are equal. Okay. So hence here in case of microcanonical ensemble, partition function, thermodynamical entropy, statistical entropy sigma and W all are equal, which represents number of quantum states or the so-called number of microstates or the so-called number of energy levels. Okay. So again I am going to suggest to all of you that you can write what we discussed somewhere with a short note. Okay. And another most important thing I want to share you that for preparation of notes for statistical mechanics, I am following this book, Statistical Mechanics, that is your Satya Prakash, and I am following this one for conceptual clear. You can keep this book. This one, another book I am referring, that is Evelyn Guha. This is a Satya Prakash book. And another book very good for your BSc. This book is not only for the BSc. This book is for BSc and MSc. Means it is recommended for the MSc. Okay, and also this will be also MSc and BSc both. And who among of you are interested to do MSc in your future, they can be buy this book also. Okay. And another book I want to recommend to you, that is very good book. I don't have right now. My younger brother has been taken to study that one. That book is that is your Birjilal Subramaniam S. Chand publication. Okay, I am going to show you the its front page image. This is the front page image of this book. You can buy this book and keep with yourself for BSc. It is very good book for the BSc. Okay, so for the preparation of the note, I am referring this book and your Birjilal Subramaniam. That is whatever I told. And here also you can refer the KP book, that is your Statistical Mechanics. This is the book of the front page, and the Basic Statistical Mechanics belongs to Pragati Prakashan. Also you can refer. These two books are very good for your exam point of view. Means in short, they are discussed. Means they have been covered detailed your syllabus. They given as per your syllabus. These two books, KP and Pragati. Okay. Two videos. After another 2 classes, I am going to give you this classification. Okay, after completion of all the canonical ensemble, microcanonical, canonical and grand canonical ensemble, I am going to give you this one. This is the classification between the 3 canonical ensemble. Here you can see that probability density is constant for microcanonical ensemble, and probability density for canonical ensemble is your a to the power minus e by kt. Already we have been discussed. You also can check your note. For microcanonical, sigma is constant. For canonical, e to the power, this was a to the power minus e by kt. For grand canonical, it is mu n minus e by kt. Okay, exponent mu n minus e by kt. It is somewhat some constant. So here, this one we have been discussed when in this topic. You can refer this video. Okay, and here you can see partition function microcanonical ensemble is nothing but del. It is written del gamma. Okay, del gamma. So you can say, sir, you can ask, sir, you told that it is del tau by h to the power 3n, and here it is gamma. Again, I am going to tell to you. Also, I told already. I have been told to you that in our note, I have been taken tau is the symbol for your phase space. In this Satya Prakash book, that they have been taken gamma symbol for phase space representation. Okay. In our note, I have been considered that tau is the phase space representation. But in this book, they have been taken gamma symbol as the phase space representation. Okay, so so you can again ask, sir, if gamma, then only gamma here it is written, and you are telling that it del tau by h to the power 3n. See, you can see that some books they are written the hypersphere is nothing but the volume of the hypersphere is nothing but the your partition function. Some books are written this one, number of microstates inside the hypersphere is your partition function of the microcanonical ensemble. So it will be somewhat differ. So in that way also you can consider that if this volume is increases. Suppose we are going to consider one system to another system. For this system, this volume, delta volume is larger than this. So obviously for this system, the number of microstates is going to be increased as compared to this one. So only for that, different books has been represented that the so-called volume, or some books are there written del tau by h to the power 3n, or some books are written w, some books are written this one sigma is the so-called partition function of your microcanonical ensemble. Okay, so after completion of these three, I will give this table that you have to write. Okay, so now we have to, yes, again I'm going to say to you, whatever we discussed about microcanonical ensemble partition function, you just write whatever we have been discussed about partition function of microcanonical ensemble. Okay, now we have to go for the partition function for canonical ensemble. Okay, partition function for canonical ensemble. I strike this one. Okay, so put the heading. Let's start. Okay, previously we found that density of a probability distribution, or probability that the number of systems or phase point in a given infinitesimal region having volume d tau of tau space or your phase space for canonical ensemble is this one. So where we got this expression? Here. We got this expression here. And the topic was, you can refer that video. The topic was this one, density of phase points in a canonical classical ensemble. In this topic, wherever we discussed in that video or in that topic, we found that for microcanonical this is constant, for canonical ensemble this is a e to the power minus e by kt. Okay, and here I suggest that you go there wherever you written this one and you just correct this one. At that time I written Gibbs free energy, this is C1. Okay, the expression is rho equal to e to the power C1 minus e by C2. Here C1 at that time I written that Gibbs free energy. You just correct that was actually Helmholtz free energy. Mistakenly I have been written at that time. Go there and correct first. It will be Helmholtz free energy, that is F. Okay, C1 equivalent to Helmholtz free energy, not Gibbs free energy. Go there and correct it. Okay, there at that time we found rho equal to a e to the power minus e by kt, which represents what? Density of a probability distribution, or that probability that the number of systems or phase point in a given infinitesimal region. This much we got previously. Okay, or instead of a we can write c here, e to the power, this will be e to the power c1 by c2 into e to the power minus e by c2. Here e to the power c1 by c2 is nothing but, sorry, e to the power c1 by c2 is nothing but we have been substituted as a. So instead of a we can write e to the power c1 by c2, nothing but kt, right? So here a can be written as e to the power c1 by kt. Just I written just reversely. Okay, so c1 is nothing but your Helmholtz free energy. That means F can be written as e to the power f by kt into e to the power minus e by kt. Let it is your equation number 1. Previously we found the Helmholtz free energy is nothing but F equal to minus nkt ln z. You can refer the previous note wherever we have been discussed partition function and thermodynamical quantities. There we have been found that Helmholtz free energy is nothing but your minus nkt ln z. Okay, that f value here we can substitute, or that value I have been written here. Okay, this minus nkt ln z. Here this z is called as partition function of a gas molecule, here I written a mistakenly, of a gas molecule. Carefully you have to watch now. This z is called as the partition function of one gas molecule, and this expression can be written in this way: minus kt ln z to the power n, f equal to minus kt nkt minus nkt ln z. Okay, here this z represents partition function of single molecule, one molecule, right? And this expression can be written as f equal to minus kt ln z to the power n, right? Okay, here this z is represents partition function of single molecule, and this z to the power n is nothing but your partition function of molecules, n molecules. Here n, capital N, represents number of molecules, partition function of n number of molecules. So this only z represented as partition function of single molecule. Z to the power n is represents as partition function of n molecule. Okay, so here z to the power n represents partition function of gas. Here just write having n molecules, Okay, here f equal to minus kt ln z. Here z equal to z to the power n. Now you can ask, sir, here z to the power n, why I have been written z? Only for that I have written here z to the power n also z, because most of the books they have written in this format. So whenever you are going to refer the book, you are going to be confused. But actually this z, if we are going to represent, see, carefully you have to watch this one. See, f minus n kt ln, suppose I am going to consider f, no problem. So this, instead of this z, I have to represent f. This f is nothing but your partition function of a molecule, and f can be represented minus kt ln f to the power n. So this f to the power n can be written as ln z, which will be called as partition function of gas having n molecules. But here I written the same thing, means for gas molecule, for single gas molecule I written z symbol, and for n number of molecules also I written z, because I kept same writing as comparing with your Satya Prakashan book. Okay, and in the forthcoming section you can found it is also represented in this way. So don't be confused. Okay, you got, I hope you understood. Okay, so here I am going to explain once again that this z is represents, if n will be here, now this z represents partition function of a gas molecule. N move to here, z to the power n is all called as the partition of gas molecules having n number of molecules of gas, partition function of gas having n number of molecules. and here I written z equal to z to the power n. Okay, so here you should not be confused. I represented in the same symbol. Don't be confused. Okay, somebody can be represented in this way also, no problem. Okay, so now here we found f equal to how much? Minus kt ln z. Here z means z to the power n. Okay, that implies minus f by kt will be equal to ln z. Then z will be equal to e to the power minus f by kt. Let it is your equation number 2. Now we have to put this value in our equation number 1. You can see in equation number 1, this is your e to the power f by kt into e to the power minus e by kt is your rho e. Here we found z equal to e to the power minus f kt equal to z. Okay, so that implies from this equation number 2, here I not written, that implies e to the power only f by kt will be how much? 1 by z, correct? Here I not written, you can also write here. That implies that implies we can write 1 by z will be nothing but e to the power plus f by kt, also your equation number 2. Write it. Okay, so now we have to use this equation number 2 in equation number 1. Instead of e to the power f by kt, we can use 1 by z. So now the equation number 1 will be rho, which is the function of e, will be equal to 1 by z into e to the power minus e by kt. Let it is your equation number 3. But by applying normalization condition, we know that this represents the density for a particular, for a unit volume, that is d tau. If we are going to consider entire volume, the probability should be equal to 1. This is nothing but representation of the probability distribution. Okay, if we have to consider, you just recall the quantum mechanics. Psi star is nothing but called as psi mod square. This is nothing but rho, probability density. And if we are going to consider entire space, psi star, entire space dx, suppose along x-axis only, dx or rho dx will be how much? 1. That we have been already studied in our quantum mechanics. That means whenever we are going to consider normalization condition is nothing but psi star dx in all the space, or you can say minus infinity to infinity, or whatever the range it has to be given in the question or problem, should be equal to 1. What is the representation of this one? This is nothing but your what? Psi mod square or rho, that is your probability density, right? These things already we have been studied in our quantum mechanics. So here this represents probability density rho here. So now if it is so, then its normalization condition means entire volume. If you are going to consider entire volume, integration d tau means entire volume, entire space or entire phase space should be equal to 1. That is the condition, right? So here rho e, we can put this one here. It will be 1 by z into e to the power minus e by kt into d tau will be equal to 1, and z will be equal to e to the power minus e by kt into d tau. Let it is your equation number 4. So this z can be accepted as the so-called partition function of your canonical ensemble. However, here this partition function is only useful for your distinguishable particle. Okay, the equation number 4 represents the partition function for canonical ensemble, but this equation needs 2 corrections, because whatever we have been considered here, the expressions, these are for distinguishable particle, but previously we have been studied and we found in case of Gibbs paradox, in case of microcanonical ensemble, at that time we found that the entropy will be, whenever we are going to consider the universal entropy, at that time we have to divide the factor n factor. We have to n factorial factor is going to be divided with the partition function. These things we have been studied in our Gibbs paradox and also in our last class microcanonical ensemble, because in case of non-distinguishable particle, this n factorial has been added extra, so only for that we have to divide. How it is, why it is, in detail we have been discussed in Gibbs paradox and in the last class. Okay, you can refer those videos to know why we have to divide n factorial. So here this partition function is not going to be accepted for both distinguishable and indistinguishable particles. Only for the distinguishable particle it has to be accepted, but for all the way it has to be accepted if the two corrections has been done. So as the phase point could not exactly localized in the phase space, but it is enclosed in a volume h to the power 3n, hence this factor should be divided by h to the power 3n, right? As already many times we have been discussed, in the phase space, this is the phase point. Actually we could not define its exact location at a particular time. Its location is going to be vary in a small volume, according to Heisenberg uncertainty principle. How it will be also we have been discussed in this topic, you can refer that video. So this phase point is going to be in the form of uncertainty, could not be give exact location. It will be in the form of uncertainty of position dx and dpx, in the form of uncertainty. So due to this uncertainty, according to Heisenberg uncertainty principle, this volume, if the phase space having n number of particle, then this small volume where the phase point will be in the form of uncertainty, okay, in the form of uncertainty, that volume will be nothing but h to the power 3n. This volume has to be divided, right, with the expression whatever we found in equation number 4. Then as we discussed previously in Gibbs paradox portion, this is, there is no bracket, for this indistinguishable particles the partition function should be divided by n factorial. Here also same concept has to be considered. Now the corrected expression of partition function for canonical ensemble will be 1 by n factorial, again 1 by h to the power 3n, has to be multiply with this factor, that is with your equation number 4. So hence it will be 1 by n factorial into h to the power 3n integration of e to the power minus e by kt into dt. This is your universal accepted partition function for canonical ensemble. This is in the form of classical, because in the classical we are considering energy in the continuous format, but in quantum mechanics, in case of quantum concept, this energy is not continuous, has to be discrete, so it will be represented in this way. In case of quantum, this z will be represented by this way, classical it will be represented by this way. Okay, now we have to go for the perfect monoatomic gas in canonical ensemble. Okay, what will be the value of this one? This is the classical partition function, sorry, canonical, yes, classical partition function of canonical ensemble. So now we are going to simplify this one, just we are going to simplify, and how much the value we are going to get, that we are going to discuss, and at the end we are going to found that z will be this one. Okay, so let's start. So we found the classical partition function z for a canonical ensemble is given by 1 by n factorial h to the power 3n whole integration e to the power minus e by kt. This is Boltzmann constant, absolute temperature, kt d tau. Let it is your equation number 1. For perfect gas, there are no mutual interaction between the molecules. For perfect gas, there is no interaction. So we have the energy is going to be added individually. Okay, each of the energy is going to be added individually. So total energy will be, because we know that E equal to P square by 2m. So total energy will be Pi square, P1 square by 2m, P2 square by 2m, like that. So it will be added individually. Each and every molecule's kinetic energy is going to be added, and the total energy will be all the addition of the kinetic energies. That is your Pi square by 2m summation over I equal to 1 to k. Here I not written k, I Pi square by 2m, and the tau is nothing but this is d tau I. This is the product summation. Okay, product summation. That means dq1 into dp1, dq2 into dp2, up to n. Okay, sorry, up to 3n. Here I written. Wait. So you can write here 1 to 3n dqi dpi. Okay. So that implies e to the power minus e by kt will be equal to how much? Will be product summation I e to the minus pi square by 2m kt. So here you can see that suppose we are going to first, here one step has been omitted. I can show you here. So here I have to write e to the minus e by kt. That means e to the power, instead of e I have to write how much? Minus pi square by 2m pi square by 2m by kt, right? So here we have to write that this will be e to the power minus p1 square by 2m into 1 by kt plus p2, kt can be divided commonly, kt. So p2 square by 2m plus p3 square by 2m, like that. So this can be represented also as e to the power minus p1 by 2m into e to the power minus kt by divided by kt, p2 square by 2m into 1 by kt into e to the power minus p3 square by 2m into 1 by kt, like that. Or this can also written as product summation e to the power minus whatever I written, minus pi square by 2m kt. Okay, so here I omitted that step whatever I explained. So now then equation number 1, now it will be how much? It will be this one, 1 by n factorial h to the power 3n. It is constant. Here it is integration over product of I equal to 1 to 3n. This one e to the power minus e by kt can be represented by this one, product of I equal to 1 product summation 1 to 3n e to the power this one minus pi square by 2m kt, right, into this one, where this one d tau product also can be written as, here product summation is there, so it will be dqi into dpi. Let this is your equation number 1. But we know that dqi, all the dqi, if we are going to add, then we are going to get vn. You got my point? See, for a particular one molecule, its position coordinates will be dx, dy, dz, sorry, dx1, dy1, dz1 for a particular particle. Okay, for one particle. So this will be how much? If I am going to integrate, it will be v, right? For if we have two particles, then it will be dx1, dx2, dx1, y1, z1 into, for second particle, dx to dy to dz to, right? So now if I am going to integrate this one to the whole volume, then how much it will be? This will be v, this will also v, so v to the power 2. Now if we have n number of particles, then obviously it will be v to the power n. Okay, so it will be v to the power n. Now therefore equation number 2 will be written as v to the power n, instead of summation, product summation 1 to 3 n dqi, v to the power n taken outside. So we can found here integration means in all the space, that means minus infinity to infinity, we can get e to the power minus pi by pi square by 2 pi kt 2m kt into dpi, okay, to the power 3n. Okay, got my point? See, for 1 we are going to get e to the power p1 square by 2m kt into dp1, and for another particle it will be e to the p1 square by 2m kt into dp2. So here, as the particles are identical and we are going to consider the momentums are equal, or if we are going to consider see, simply you have to just accept I to the 1 to 3 and dqi is considered as v to the power n, right? So here the another terms will be integration of I equal to 1 to 3n e to the pi square by 2m kt into dpi, this one. And this integration I told is to be all the space, means minus infinity to plus infinity. So e to the power pi square by 2m kt dpi whole to the power 3n. So for each particle we are going to get one term. So for 3n times it will be 3n times we have to consider, so it will be to the power 3n, right? Let it is your equation number 3. Now we have to evaluate the integral, that is minus infinity to plus infinity, this one. Okay, how much it will be? So we know that in bracket you have to write, we know that minus infinity to plus infinity in general, okay, y to the power n e to the power minus ay square dy is nothing but your 2 into 0 to infinity y to the power n e to the minus ay square dy. Just multiply 2 whenever n equal to even, for n equal to even. But if n equal to odd, then this integral value will be 0. This integral value, the integral value will be 0. You just write, for if n equal to 0, the integral equal to 0. Okay, and here now we have to consider n equal to 0. N equal to 0 means it is even. So y to the power 0, here y to the power 0 e to the minus ay square dy into 2. Suppose y to the 0 is there. Y to the 0 means 0 is a even number, considered as even number. So it can be written as 2 into 0 to infinity y to the power 0 e to the minus ay square dy, right? And equal to 2. And then this value is how much? This value is this much value, which is 1 by 2 1 by a to the power n plus 1 by 2 into gamma n plus 1 by 2. How it is, why it is, we discussed with a separate video. You can refer to my channel, full integration named as, you can refer that integration, useful integration करके एक video है. Okay, you can refer that video named as useful integration. So how this will be direct this one, there I have been explained. That means 0 to infinity y to the power 0, or you can see this one y to the power n e to the minus ay square dy, it will be 1 by 2 into 1 by a to the power, this is a to the power n plus 1 by 2 into gamma n plus 1 by 2. So this integral value will be this one. So now here if we are going to consider this integral, then how much it will be? that will be also 1 by 2, 1 by a to the power n plus 1, gamma n plus 1. See, wait. So here it will be 2 got cancel. So we are going to get 1 by a to the power n plus 1 by 2 into gamma n plus 1 by 2, this much, right? Now what will the value of this? Here n is, for this case, n is 0. So a to the power 1 by 2 means root over of a. And here gamma, n is 0, gamma half will be root pi. So root pi by root a, we can found the integral of integration value of this one. This integral value will be root pi by root a. Okay. Sorry, I told that. That means minus infinity to infinity, y to the power 0 to e to the power minus ay square by dy will be root pi by root a. Got my point? Minus infinity to infinity. If n is even, it will be 2 into 0 to infinity, this one. For n equal to 1, then integral will be 0. Sorry, n will be odd, integral will be 0. Then here, this integral value will be nothing half of 1 by a to the n plus 1 by 2 into gamma n plus 1 by 2. 2 got cancelled. It will be 1 by a to the n plus 1 by 2 into gamma n plus 1 by 2. So if we are going to consider n equal to 0, that means only this integral, n equal to 0. If we are going to consider n equal to 0, here in general we found a to the power n plus 1 by 2, gamma n plus 1 by 2. If n equal to 0, then it will be a to the power 1 by 2, gamma 1 by 2. Gamma 1 by 2 value is root pi, and this will be a to the power 1 by 2. So hence we found this one. Hence we found, you can refer that video. In that video in detail, by considering gamma function, we done that one. Okay, minus infinity to plus infinity, y to the power 0 into e to the power minus a y square dy. The value will be how much? We found root over pi by root over a. Okay. Now we are going to use this integral value by considering here your y is nothing but how much? Pi. If we are going to compare this one and this one, here pi square is there, y square is here. So here y is equivalent with pi, right? Okay. Here a will be equal to, 1 by 2m kt, right? 1 by 2m kt. Got my point? If I am going to compare this integral with this one, so the pi will be y and a will be 1 by 2m kt. 1 by 2m kt. So hence integration of minus infinity to plus infinity, this one, e to the minus pi square by 2m kt into dpi, okay, can be written as minus infinity to plus infinity, pi to the power 0 into e to the power minus 1 by 2m kt into pi square into dpi. So this is nothing but is your a as compared with this one. So finally the value of the integral will be how much? It will be root over of pi by root over of a. That means root over of pi by a is nothing but 1 by 2m kt root over. That means it will be 2m pi kt root over, right? Same thing it has been written in the next page. That now consider this integral will be 2 into 0 to infinity, minus infinity to infinity, this much is nothing but here you can write another step, it will be better. 0 minus infinity to plus infinity, pi to the power 0 into e to the power minus pi square by 2m kt into dpi, okay, will be equal to 2 into 0 to infinity. No need to write this one again. Into e to the minus pi square by 2kt, because pi to the power 0 is 1. No need to write down once again, or I suggest that you can write pi to the power 0, you can write. Okay, so e to the power minus pi square by 2 mkt dqp. Here I written, okay, here I written, no need to write here. Here no need to write. Here I written. Next step I have written pi square, pi to the power 0, e to the power minus pi square by 2 mkt. So this value is nothing but how much? 1 by 2m, 1 by 2 into 1 by a to the power n plus 1 by 2. Here a is nothing but 1 by 2 mkt to the power n plus 1. N is 0 plus 1 by 2, gamma n plus 1 by 2. Okay, so it will be 2 got cancel. It will be 2 mkt root over into root over of pi. This is nothing but 2m pi kt, or 2m pi kt to the power 1 by 2. Okay, hence the equation number 3 will be, equation number 3 will be how much? This one, b to the power n 2m pi kt to the power 3n by 2. So to know the detailed integration about this, you can refer that video, whatever I told. Okay, so now this, let this is your equation number 4. According to definition of thermal de Broglie wavelength, lambda is equal to h by 2 pi kt to the power 1 by 2. See, this is nothing but dimension of momentum, and we know that according to de Broglie, lambda is equal to h by m into v, right? Here m is there, 2 pi kt is nothing but, you will give your the dimension of the velocity. Okay, that means the denominator term is the dimension of the velocity. So this term h by 2 pi mkt is represents thermal de Broglie wavelength. Thermal de Broglie wavelength, why it is named so? Because whatever we are discussing statistical mechanics is referring the thermodynamics, right? So thermodynamics means, suppose a gas molecule is moving. Is moving means whenever it is moving, it has a wavelength according to your de Broglie. So what will be the when if it is moving with a high speed, then it has the momentum, then it has the de Broglie wavelength will be lambda is equal to h by mv. So that is nothing but called as thermal de Broglie wavelength, as it is linked with thermodynamics. So lambda will be equal to h by 2 pi mkt to the power 1 by 2. Now equation number 4 will be written as v to the power n by n factorial, and this collectively can be written as 1 by h by 2 pi mkt to the power 1 by 2 whole to the power 3n. You can see it will be h to the power 3n, it will be h 2 mkt to the power 3n by 2. It will move to numerator and we can get this one. So now again with arrangement we can write z equal to v to the power n by n factorial. This is nothing but lambda. So lambda to the power 3n, right? So z will be equal to 1 by n factorial. Here you can see v to the power n, and this is lambda to the power 3n, can be written as v by lambda q whole n. Let it is your equation number 5. Here z is purely translational of gas, is purely monoatomic. Okay, that means this partition function represents the distribution of gas molecule with moving with translational motion only, and the gas molecule consists of purely monoatomic particles. Okay, whatever we are going to consider the molecules, gas molecules in the vessel, these are purely monoatomic. Okay, monoatomic. Now further simplification we have been done, nothing else. So from equation number 4 we can get, from equation number 4 also we can write v to the power n by n factorial 2 pi mkt to the power 3 by 3n by 2, 3n by 2 by h to the power 3n. That is your equation number 4. Again I written. Now this is can be written as 1 by n factorial v by hq 2 pi mkt to the power 3 by 2 whole n, right? Whole whole to the power n. So V by HQ 2 pi m kt to the power 3 by 2 is what? This is what? This is the partition function of a single particle, monoatomic, of a single particle. This is the value of the partition function. I am going to show you the expression. You can check your note, previous note, whenever we have been discussed this one. After just partition function, we discussed this one, partition function for translation motion of a gas molecule. How much value we found? We found V into 2 pi m kt by h square to the power 3 by 2, right? Or you can see this is V by HQ 2 pi m kt to the power 3 by 2. This is the value we found. So here this represents what? This represents what? Here I have to write. You can write. Here I written. You just write. I am going to zoom it that you can read well what I written. Then the term in square bracket. Then the term in square bracket represents the value of partition function of a molecule. Okay, of a molecule or a particle for translational motion. Okay, so now it can be written as again z equal to f to the power n, f to the power n by n factorial. Okay, so here f is nothing but V by HQ 2 pi m kt to the power 3 by 2 or V into 2 pi m kt by h square to the power 3 by 2. Any form you can write or remember. So or we can write V by lambda q. Okay, V by lambda q, and which is, this is f. F is the one particle partition function. I told initially whenever I discussed these things that here for one particle it can be written as f. Instead of writing z, we can write f. But to equalize the book Satya Prakashan and other books, they are not mentioned, but here they are mentioned. Okay, you just don't be confused that here in this expression this z is represents partition function of a gas molecule, but here if I am going to take this n to here, this is nothing but z to the power n. Z to the power n is represents partition function of gas having n number of molecules. Okay, same thing in other format it has written here. For a molecule it is represented by small f. The value is V by HQ 2 pi m kt to the power 3 by 2. This expression you just remember. This is most important for your doing the problems. Many questions asked in your entrance examinations. Only just to write down the partition function of a single molecule. So different options will be there. Just remember V by HQ 2 pi m kt to the power 3 by 2. So for n number of particles, for n number of monoatomic particles, it will be just divide n factorial and to the power n. That's it. So this is in the another form V 2 pi m kt by h square to the power 3 by 2, and it can be represented. This is also nothing but 1 by lambda q, which is one particle partition function. So here we have to stop our discussion in our today class. In next class we are going to discuss thermodynamical functions or quantities for canonical ensemble in term of partition function. So here you can see Helmholtz free energy in term of Z. Here Z we have to use f to the n by n factorial, and entropy. Whenever we are going to evaluate the entropy in case of canonical ensemble, also at the end we are going to get the same the Sacquet tetroid equation, right? Directly, because initially we have been rectified the partition function by dividing n factorial and h to the power 3n. So whenever we have to just use del f by del t at constant v, directly we are going to get the Sacquet tetroid equation. Okay, now then we have to discuss internal energy and internal energy. That's it. Three functions, thermodynamic functions, and or the so-called quantities for canonical ensemble that we are going to discuss in our next class. Okay, so thank you so much for watching this video. I will suggest that carefully watch the video and write down the note for exam point of view. Okay, thank you so much. Thank you.